It's our first time presenting here at DFRWS. It's also my first time and Aaron's first time attending. So we're pretty excited to be here. I'm Tom, this is Aaron. We both work at Google. We do forensics and incident response. So this basically means that we write a lot of code because we're lazy and we like to do things automatically. Aaron is the core developer of Turbinia. I'm one of the core developers of DFTimeWolf, which we will introduce in a bit. We're in this sweet position where we can write a lot of code and also use the same code that we write in our daily incidents. So that's pretty cool because we don't have to follow feature requests. Well, we do between both of us, but most of the time we can get, since we're in the same team, we can get things solved pretty fast, and we really know what to expect and what we want our tools to do. So that's pretty cool. And both of our ambitions, and I guess the same goes for the rest of the team, is to automate ourselves out of a job, to be able to spend most of our time doing actual forensics investigation and analysis, rather than fight with things that don't work. So why are you guys here? You're going to learn about most of our toolkits that applies to everything cloud. So everything that we're going to present is free and open source software, so you can use it in your own infrastructure, in your own projects. And since presentation of all tools can be a bit boring, we'll try to articulate all of these with a scenario of sorts. So we're going to focus on DFTimeWolf, which I mentioned, Turbinia, which I mentioned. We're also going to talk about Lasso and TimeSketch. It's going to be a lot of things to cover in the 18 minutes that are left. So we're going to quick show of hands. Who's heard about log2time and Lasso? All right, that's a lot of people. That's good. So you all know how it works. It basically builds a big timeline out of things it encounters, files, file systems, etc., event logs. It's going to extract timestamps and try to build a nice, neat timeline of things that happen on the system. Who knows about TimeSketch? Also pretty cool. So TimeSketch plays really well with Lasso, as well as it should, because our team develops both. It's basically a forensics timeline visualization tool, so it's some sort of enhanced grep, which is pretty cool because you can see several timelines that you extracted with Lasso on different systems. You can all see them in the same time span, so this is pretty useful when dealing with large-scale investigations. It's also multi-user, so you can have many users on the same TimeSketch instance collaborating between each other. Multi-case, you can have several sketches in the same TimeSketch instance for different incidents, and also multi-timeline, so you can timeline many systems and have them all in the same sketch, so you can easily draw associations between each other. I mentioned DFTimeWolf. Who knows about DFTimeWolf? Well, that's a few people. That's pretty cool. Thanks. So DFTimeWolf is basically everything that glues together our toolset. If it has an API, then DFTimeWolf can talk to it and can make sense out of how to use it. So basically it works with modules. Modules are just very simple Python classes that interact with the different APIs. And so you can have collectors. So for example, if we need to query GER, we can have a GER collector. We can have a class of processor that's going to process the evidence that came from GER. And we can have a TimeSketch exporter that's going to export whatever file the processor gave it. So everything is articulated with what we call recipes, which is basically a very small JSON dictionary that explains the details how to chain all these modules. And we're also going to talk about Turbinia, and I'll let Aaron talk about this.
Hey everybody, I'm going to talk to you guys about Turbinia and some of the work we've been doing over the last year on this project. It's an open source project similar to all the other ones that we're working on. You guys hear me okay? Yeah.
It's all the Creek.
Is that better?
Yes.
Awesome. Yeah, so what we want to do with this is automate a lot of the common tools that we use every day. We want to be able to do this at scale, and we also want to be able to do this not just in the cloud because it gives us some nice scaling properties, but also on the cloud, meaning actually processing forensic artifacts from the cloud itself and process as we move, people moving more of their infrastructure into the cloud. We want to be able to process that for the rest of our tools to keep up with that. A couple other notes about this. This was originally conceived by Johan and Corey a couple years ago. They wrote an initial proof of concept about a year and a half ago, maybe. We started rewriting that and kind of re-architecting that a little bit. And yeah, this is the, we're not actually very good at logos here. This is the first logo that we came up with, which we affectionately refer to as the flying ham. Unfortunately, we came up with the one we have now, which is a little bit great. Yeah, so we can install this in different environments. Cloud is kind of the main use case that we have, and makes everything's in the cloud. All of the evidence that we store, all the processors, and we use the cloud infrastructure. We also have the ability to put this in kind of a hybrid environment. So like the infrastructure pieces are still in cloud, so you don't have to maintain those. But then the workers and storage stays locally. So you don't have to push all of your data to the cloud, but you get some of the benefits of that. And then finally, just in the last couple months, we have this local version of Turbinia, so you can keep everything completely local. That was contributed by Eric at Facebook, and that uses some other, Celery and Convo for messaging, and yeah, it's kind of nice because then you can have it all on premises. Here's the overall architecture. I'm not going to spend a lot of time on this, but you can see the clients can make requests to the server through PubSub. The server then schedules tasks also through PubSub, in this case using the PSQ library. Workers pick up those tasks and can talk to the evidence storage, which in this slide, this is the cloud version, so this is all in cloud, in GCS or persistent disks. And then the server stores its state into data store, and then we can query that from the clients through cloud functions. So it's kind of nice because this is all in the cloud, and from the client's perspective, you can have a super lightweight client that can just talk PubSub and cloud functions. Here's a hybrid version, which is basically the same, except for you can see at the bottom, the workers and the shared storage is moved off, but we can still leverage the rest of the functionality in the cloud. And then here's the new local version. Very similar diagram, except for you have the components replaced with Convo as the messaging interface, Celery is the task scheduling, and Redis is kind of the storage that clients can talk directly to. And then the same here, the workers are also local along with all the storage. Obviously, there's some pros and cons to doing this. The cloud is nice and it can scale up. You don't have to manage that infrastructure, but it's a little bit difficult to get some evidence in and out of the cloud. If you've got like a lot of big raw disks, it can be a pain to copy it up there. So in our environment, we've got a couple different installations, and we can push things to whatever makes sense, whichever instance makes sense. For the hybrid as well, only the metadata goes up to the cloud, but then everything stays local, so you can just have everything on shared storage. Local, again, everything's local. So evidence. In this case, what we mean by evidence is really anything that we want to process. This can be a raw disk, a cloud disk, a PLASO file, anything that we can define metadata for. And these are all defined in Python. The tasks, when they run, generally when we make a request into Turbinia, it's to process something like a disk. As when the tasks are processing this, they can generate new evidence that gets fed back into Turbinia that will get mapped against jobs that can process that, and then tasks can get rescheduled to process those, and that kind of generates a tree of processing that happens. The evidence, as far as the client and server is concerned, is really just metadata, and then the actual storage for that, the metadata contains pointers to that, paths, and everything's actually stored in some type of storage or cloud. We have pre and post processors that can make this the evidence available to the tasks. So, for example, a cloud disk can attach it. A nice property of this is that the evidence types can be kind of stacked. Because this is all in Python, you can have, the example I have here is a cloud disk raw embedded, and what that is a persistent disk with a raw disk inside of it, so that the outer disk can be mounted first, and then the parent class's preprocessor can be run to mount the inner disk, and then we can continue down that chain. For example, one of the things we want to have soon is support for encrypted disk, and that's just kind of another layer in that process. The output manager, because we're running in cloud, we need to be able to copy things back and forth. So this basically just copies things when the task comes up and you need access to evidence. It can copy that into the task, and then conversely, when new evidence is generated, it can copy that back to storage. So a typical workflow is the client sends a request to the server. The server maps that against jobs that can process that particular evidence type. And it creates tasks which get scheduled, and then a worker from the worker pool will pick that up. It'll copy that if needed, it'll pre-process that, and then it will actually run the task itself to process the evidence. And then, as I mentioned, it can generate more evidence and send that back into Turbinia. I mentioned earlier this kind of creates a graph of different jobs. This is actually a auto-generated graph from the code, and you can see that the rectangles are evidence, and they are mapped to jobs, which generate more evidence, and then that kind of flows all the way from a disk down to like a text file. Creating new tasks is easy now that the infrastructure is there, even if you're not a super strong coder. For like a simple execution task, it's just 15 lines of code. There's some other boilerplate code, but documentation is at the link there. If you guys are interested in adding things. And then just a quick note on the scope here. For Turbinia, all of the orchestration and things that happen externally, like with TimeWolf, I'll show you a demo of that. But we intentionally want to limit the privileges that Turbinia has. I mean, we could have it go out and grab all of these things from different places, but we actually want to push things into Turbinia rather than have it pull it. And then we use TimeWolf to push that. Next steps, we've got a lot of things we want to do with this. Support encryption, we want to add reporting to the tasks. This quarter we're focusing a lot on adding new tasks. We're doing kind of like analysis. We want to add recipes similar to what TimeWolf has, so we can make it a little bit more configurable. And some of the code, the very last demo that we're going to show you, we still have to polish up and publish to our external repo. So that's coming. Everything else is in the open source in GitHub. So just real quickly, the big picture here. This is again kind of like end-to-end with our tools. We didn't talk much about Ver, but that's kind of like an endpoint. We can pump on systems and pull data back from that. We can use TimeWolf to go out and grab that from Ver. We can grab things from cloud, and then we can push that to our processing here with Turbinia. And then finally, after the processing happens, we can push timelines of things like that into TimeSketch. I put this iceberg image on here just because I really wanted to make the point that a lot of the stuff, automation and things we're doing, is built on a lot of other tools and a lot of time and effort. And like this has been years of all these other parsers with Lasso, TSK, all these things that we depend on made this possible. So with that, I'm going to introduce our scenario, and Tom's going to talk a little bit about the demos we're going to do.
So let's talk about the scenario that we chose. So just FYI, none of what I'm going to talk about next is true except for the demos. So please don't freak out if you see people being compromised. So the victim that we chose is Greendale Poly, so it's a very famous fictitious university. Everyone's on semester break when suddenly someone gets a tip and the admin reports, a suspicious domain. So it's Greendale.xyz with one E. And well, this is the scenario, and now Greendale has been migrating conveniently all their infrastructure to Google Cloud. So this is where all of our tools can become very useful. So if we look at this, we can think, okay, Greendale, that looks pretty targeted. We want to look for related artifacts, and let's explore a bit what our forensics options are. So this is the first demo. Basically, what we're going to do is run DF TimeWolf on a cloud instance in a cloud project, always GCP in this case. And this will create the GCP_forensic recipe, as you can see here. It will create it will bootstrap an analysis VM in another separate project. It will grab a snapshot of the disk that exists already in the allegedly compromised instance, which is Green admin here, because we want to check if the admin has clicked on any links. And it will create a disk it will create a copy of the disk to Green as this Green copy. So what can we do with this? This will also create an analysis VM that we can SSH into. And we already have all our tools available there, like FLS, and the disk, the allegedly compromised disk, is already attached. So you can just do FLS on that if you want, and you can start doing forensics right there. What if you want to do things a bit more at scale with Turbinia? Exactly what Aaron is going to talk about now.
So this is the demo we have for Turbinia. Let's see here. Just to set this up real quickly, we've got 3 different windows here in a debug session. We have a client, that's kind of the view you'd actually have as a client. And I put the server and worker here just so you can see kind of what's happening. And so we make the request to the server, and you can see here that there's specifying a keywords file. In that keywords file, we put the grendale.xyz domain, and that's going to filter some of the output for this, and we're processing a cloud disk. And we have the other parameters for that. We can see that the server picked up that request. It's mapping it against the different jobs, and then now we can see it's scheduled Plasso task. That got picked up by worker. We can see Plasso is running, and it's going to generate a Plasso file. And send that back to the server here in a second. The server is going to map that against jobs, and then it's going to create some other jobs as a result of that. One of those jobs is the rep task, and it's going to take the keywords that we entered in the first step and filter the output and generate a second filtered list of output here. Again, at the client, at the bottom there, we can see how many tasks have been run. And then what I do here is I just look, it's a little squished on the screen here, but I take the filtered output from there and look at it, and then we'll be able to see we can see here that there's a curl pipe bash to our domain, the bad domain here. So that is Turbinia. Everything's fine. So this I'm just going to go through. We kind of already talked about this. We're out of time, so I'm not going to go through all this. But we're DF Time Wolf is copying the disks, sending it to Turbinia. And what I really want to show you here is the last demo, which really combines all the stuff. This is the part that we've been kind of working on the last few weeks that just got completed or almost complete enough to make a demo of it, and we'll polish that up and publish it soon. But this is going to look very similar. It's a very fast demo. It's very similar to the first one. We specify a separate recipe, the GCP Forensics Turbinia recipe, and then we specify all the same cloud information to specify that. We could also potentially specify all of the other instances to automatically do this at scale. But we see basically similar to the first demo, where I copied the disks. Then it sent a request to Turbinia a little way in here, and then I time slice this to make this fast, but we can see the output from that. And then at the very bottom, what we get here is a link to TimeSketch. And so we can actually see all the output from those previous things in TimeSketch, which is right here. And if we do a search on that suspicious domain, we can also see the output of Plasso's parsed the bash history file and found that same curl pipe bash. So I'm going to let Tom wrap up here.
All right, so fortunately no one got owned. So the payload impression was the keylogger, but we can find any traces of lateral movement, and also Greendale uses two-factor authentication everywhere, so they're all safe. We suspect the attacker's objective was to disrupt the launch of Greendale's new PhD program, and ACE flow studies, which is pretty interesting, and all the universities want it. So, We've covered a bunch of tools, but what else can they do? So we didn't talk much about here, we just mentioned it. Grid can do some host timelining and also run custom Python scripts. It's basically whenever you want to grab stuff from your endpoints, you will use Grid. Plazo, well, you can also focus processing on specific user-selected artifacts. Like you can tell Plazo, I want to grab this disk and show me all the browser history artifacts that you have, process them and give me a timeline. That's something that it can do. TimeWolf, as we've seen, you can basically chain whatever has an API to it. So if you want to augment, I don't know, your output Plazo file or your sketch with, your threat intelligence repo, then it's easy to do. You just need to write a small module, and you can automatically route the last output that you got and interact with TimeSketch. TimeSketch also has a bunch of other features like heat maps and graphs. They're all pretty cool, and I encourage you to check them out. There's a demo instance in demo.timesketch.org, I think. And Turbinia, as we've seen, it's all your go-to for repetitive and parallelizing tasks that you may want to run on 32 cores if you don't have those at home. So if you haven't been paying attention today, this is what you really need to write down and take back and write down in your report. So basically, this is all tools that you can use in your ecosystem. We've seen most examples with GCP, but you can also use them, as Aaron mentioned, like locally with other software. TimeWolf is not bound to anything related to cloud. There are some cloud recipes and cloud modules, of course, but you can also use it with Gür and other things. It's used daily by our teams, so these aren't tools that are like proof of concepts. We really use them to respond to incidents. So that's pretty cool. And we also encourage contributions. It's all open source in the next slide that I'm going to show you, and it's all Apache tool license. So here's a list of all the open source repos. It's mostly on GitHub. We also opened recently a Slack channel, open source efir.slack.com. There's a small Heroku app link that you can use to automatically join the Slack channel. It's to provide support about all these tools, but also, DFIR tools in general. As long as it's open source, we're happy to talk about it. And I think that's all for us. So if you have any questions, we're happy to take them. Thanks.
I think there is -1 minute for questions, but we can indulge one while the next speaker comes up.
So I love Plaza, and I like what I see here, especially some future discussions I think we'll have about the moving processing to the cloud. One question I have is how you're dealing with, let's say, drop messages or visible errors, and the problem of processing that's perhaps not getting completed or missing the results when they come back to some collection. I've seen this on other distributed processing systems. It's very kind of difficult to manage.
Yeah, that can be an issue. We haven't built anything in the system to try to detect that sort of thing. We try to do a good job at detecting errors and bubbling that up to the user so that the user can make that decision. So if the task fails, like we have status messages that gets bubbled back up to them. But that's something that we have to deal with too. Awesome. Thanks everybody.